In this video, we'll complete our classification of which modular bases have primitive roots and which do not. Well, what do we know so far? If we're looking modulo 2 to the k, there is a primitive root if and only if k is 0, 1, or 2. So 1, 2, and 4 have primitive roots, 8, 16, 32, etc. do not. However, if we're looking at a power of an odd prime, there's always a primitive root modulo that base. However, there's lots of other numbers, so we're going to establish a couple of theorems. First, if you have n equal to exactly 2 times a power of an odd prime, then there is a primitive root mod n. However, if n has 2 distinct odd prime factors or only one odd prime factor but is divisible by 4, then there are no primitive roots. So altogether, this totally covers everything. In the prime factorization of a number, maybe there's 2 odd prime factors, then no primitive roots. Maybe there's 1 odd prime factor, but divisible by 2 to a power, which is 4, 8, 16 or bigger, then no primitive roots. Maybe n has a single odd prime factor, but also 2 to the first, then we claim there is a primitive root. Or maybe a single odd prime factor and not divisible by 2, in which case we already know it has a primitive root. Or maybe it doesn't have any odd prime factors at all. It's a power of 2. Then we know exactly which powers of 2 do have primitive roots. So altogether, if we can just show these 2 theorems down here, we'll actually be done. Altogether, the only positive integers with primitive roots are 1, 2, and 4, an odd prime to a power, or 2 times an odd prime to a power. Everything else will fail to have a primitive root. Let's take care of the case where n is 2 times an odd prime to a power. We know that there is a primitive root modulo p to the k. An odd prime to a power always has a primitive root. So let's let a be that primitive root. It's an integer, so that the order modulo p to the k of a is phi of p to the k, p minus 1 times p to the k minus 1. Now, if a is relatively prime to our new base, 2 times p to the k, we claim it's also a primitive root mod 2p to the k. So p to the k can't be a factor of any power of a from 1 up to, but not quite including the order. This number here was the order modulo p to the k of a. So every power up to this one is not equivalent to 1. In other words, p to the k is not a factor of that difference. But if p to the k isn't a factor of that, then 2p to the k is also not a factor of that. So a to the j is not equivalent to 1 modulo 2p to the k for j starting at 1 and counting up to this number here. Therefore, the order has to be at least as large as the next number I would test. Remember, the order modulo 2p to the k of a is the smallest power of a equivalent to 1 modulo this base. A to all of these powers is not equivalent to 1. So the next number I test would be exactly p minus 1 times p to the k minus 1. So the order must be at least that large. But phi of 2p to the k is the same number as phi of p to the k. It's p minus 1 times p to the k minus 1. Because 2 is relatively prime to an odd prime power, I can use multiplicativity of the Euler-Toshin function, and phi of 2 is 1. So the order mod 2 times p to the k of a is at least as big as phi of 2p to the k. It's therefore exactly equal to it, and a must therefore be a primitive root modulo 2p to the k, under the assumption that it was relatively prime to the new base. What if it's not? Well, a is definitely relatively prime to p to the k. So if it's not relatively prime to 2p to the k, then it must have been an even number. It must have that common factor of 2. In that case, a is even. Okay, but if a is even and p is an odd prime, then p to the k is odd, and a plus p to the k will be a new odd number that's equivalent to a modulo p to the k. If it's equivalent to a mod p to the k, it's also a primitive root mod p to the k. So if a is even, then this number here is now odd, but also a primitive root mod p to the k. But this number is now an odd number, so it is going to be relatively prime to 2p to the k. Therefore, this number here will be a primitive root mod 2p to the k. All right, what if n has this general prime factorization? So we're going to write n as its prime factorization. Now, if a is a primitive root, then it has to be relatively prime to n. So it's got to be relatively prime to all of the primes in the factorization of n. Therefore, it's relatively prime to all the powers of those primes. By Euler's theorem, then, a to the phi of pi to the ni is definitely equivalent to 1 mod pi to the ni. Now, let n be the least common multiple of all of these totient function values. Phi of p1 to the n1, phi of p2 to the n2, etc. Find the least common multiple of all of them. Since n is the least common multiple of all of those values, it's a multiple of each of them. Therefore, I have here a to the capital N. That's a multiple of phi of p1 to the n1. Therefore, a to the capital N is equivalent to 1 mod p1 to the n1. But n is also a multiple of phi of p2 to the n2. So a to the n is equivalent to 1 mod p2 to the n2, and so forth and so forth. By letting this be a common multiple of all of these values, a to the n is equivalent to 1 modulo all of these bases. But all of those bases are relatively prime to each other, p1 to the n1, p2 to the n2, and so forth. These are all relatively prime. So if a to the capital N is equivalent to 1 modulo all of them, the Chinese remainder theorem tells us that any two solutions to the system, equivalent to 1 mod p1 to the n1, equivalent to 1 mod p2 to the n2, and so forth, must differ by the product of all of those bases. Therefore, n, which is a product of all of these bases, must be a factor of whatever happens to solve all of these, such as a to the n. A to the n is a solution to all of these equivalences, but 1 is also a solution to all of these equivalences. So n must be a factor of this difference. Therefore, a to the capital N is equivalent to 1 modulo n. Now, capital N is some power of a equivalent to 1 mod n, so the order cannot be any larger than that. So assuming a is a primitive root modulo n, with this prime factorization, we've established that the order of a must be no larger than capital N, the least common multiple of phi of all of these prime powers. Now, n is the least common multiple of all of those numbers, so it's definitely not bigger than just multiplying them all together, phi of p1 to the n1, etc. But phi is multiplicative. So n, the order, capital N, the order of a, cannot be any larger than phi of n. Overall, the order mod n of a is less than or equal to capital N, this least common multiple, and this least common multiple is less than or equal to phi of n. We assumed, however, that a was a primitive root mod n, in which case the order mod n of a is equal to phi of n, so all three of these things must be equal. Therefore, the least common multiple of all of these totient values, which was capital N, must in fact be equal to phi of n, but since phi is multiplicative, I can distribute it like this. Now, under what circumstance can the least common multiple of a list of numbers simply be equal to their product? Since the least common multiple of a bunch of numbers is the product divided by the greatest common factor, that means all of the totient function values must be relatively prime to one another. So for any odd prime, phi of p to the m will have p minus 1 as a factor here and therefore be even. So what can we conclude? We need all of the totient function values to be relatively prime under the assumption that there was a primitive root. How can all of the totient function values be relatively prime? I definitely can't have two of them being even. But for any odd prime, I'm going to get an even value for my totient function. So if there are two different odd prime factors, I have a problem. The two different totient function values would both be even because they'd have p minus 1 and q minus 1 as factors. But if two different totient function values fail to be relatively prime, then this least common multiple is not equal to this product, and then this order can't be as big as phi of n. So if there's a primitive root, I cannot have two odd prime factors. On the other hand, what if n has a single odd prime factor p? Well then, I end up with a p minus 1 in one of my totient function values. But then 2 to the k can't be a factor for any larger power of 2, because remember, phi of 2 to the k is 2 to the k minus 1. So if k is 2 or larger, in other words, if the number is divisible by 4, then p minus 1 would be even, and 2 to the k minus 1 would also be even, not relatively prime. This LCM is not equal to this product, this order is not equal to phi of n, and a is not a primitive root. So if n has 2 odd prime factors, nope. If n has 1 prime factor, then the power of 2 cannot be 2 squared or larger. So to wrap things up, we have shown if n has 2 odd prime factors, there's no primitive root. If n has a single odd prime factor, but it's also divisible by 4, it has no primitive root. Any odd prime to a power does have a primitive root, as does 2 times an odd prime to a power. For just powers of 2, the only powers that do have primitive roots are 1, 2, and 4. Overall, we have our result. A positive integer n has a primitive root if and only if n is 2, 4, an odd prime to a power, or 2 times an odd prime to a power. By allowing k to be equal to 0, we're sort of wrapping 1 into this entry here, but not a big deal. So let's take a look at some quick examples. For each n going from 10 to 22, let's determine if there are primitive roots or not. You don't need to actually find them, just answer, is there one or not? Well, for n equals 10, we have 2 times an odd prime to a power, so it does have a primitive root. 11 is an odd prime to a power, it has a primitive root. 12 has an odd factor and 4, therefore it has no primitive root. 13 is an odd prime to a power, it has a primitive root. 14 is 2 times an odd prime to a power, it has a primitive root. 15 has 2 distinct odd prime factors, it has no primitive root. 16 is a power of 2 that was not 1, 2, or 4, so it does not have a primitive root. 17 is an odd prime to a power, it has a primitive root. 18 is 2 times an odd prime to a power, so it has a primitive root. 19 is an odd prime to a power, it has a primitive root. 20 has a single odd prime factor, but it's also divisible by 4, so it has no primitive root. 21 has 2 different odd prime factors, so it has no primitive root. 22 is 2 times an odd prime to a power, it has a primitive root. Okay, so we have completely answered the question of which bases have primitive roots and which don't. The bases that have primitive roots are 1, 2, and 4, but no other powers of 2. Every odd prime to a power, and 2 times any odd prime to a power. If, however, a number has 2 distinct odd prime factors, it does not have a primitive root. If it has a single odd prime factor but is also divisible by 4, it has no primitive root, and that totally wraps things up. So thankfully, we have completely answered the question, what numbers have primitive roots and what don't.